Let us now take a look at electronic configurations. What does that even mean? It means that we want to describe the region of space where each electron in an atom is most likely to be found. And I want us to quickly remember that an s orbital can only accommodate a maximum of 2 electrons. A p orbital can only accommodate a maximum of 6 electrons. A d orbital can take a maximum of 10, and an f orbital can take a maximum of 14 electrons. To begin to look at the electronic configurations of each atom, we will begin by looking at the energy levels. Let us consider these 7 energy levels. Each energy level can only accommodate a certain number of sub-levels. That is another way of saying that each energy level can only hold a certain number of shapes or orbitals. Energy level number 1 can only hold one type of shape, the s orbital. Energy level number 2 can hold 2 types of shapes, s and p orbitals. But we will need to be able to distinguish between the s orbital in energy level number 1 and the s orbital in energy level number 2. To distinguish them, we will write their energy levels in front of them. The energy level number 3 can hold a maximum of 3 types of shapes. So we would have 3s, 3p, and 3d orbitals. Energy level number 4 can hold a maximum of 4 sublevels or shapes. So we will have 4s, 4p, 4d, and 4f. For introductory chemistry, we cannot go beyond f orbitals. So in energy level number 5, although we technically have more than 4 orbitals, we will restrict ourselves to only 4. So we will have 5s, 5p, 5d, and 5f. Also, n equals to 6 technically has 6 types of sublevels, but we will restrict ourselves to only 4. So 6s, 6p, 6d, 6f. And we will have 7s, 7p, 7d, and 7f sublevels or orbitals. Also, it should be noted that in the Bohr's model of an atom, 2s and 2p orbital in energy level number 2 will both have exactly the same energy. In the Bohr's model, 3s, 3p, and 3d orbitals will all have exactly the same energy. And in n equals to 4 energy level, 4s, 4p, 4d, and 4f orbitals will have exactly the same energy, because the Bohr's model only works very well for one electron systems. And in one electron system, all the orbitals at a certain energy level are equal in energy. However, when you have more than one electron, all the orbitals at a certain energy level will not have exactly the same energy. Let me repeat. In multi-electron systems, all the sublevels in one energy level will not have exactly the same energy. Let us take a look at what I mean when I said that one electron systems will have all the sublevels in a specific energy level with equal energy. Look at this plot of the energies of the orbitals in each energy level. You will notice that 2s orbital has exactly the same energy as 2p orbital. Both orbitals are the sublevels in n equals to 2. You will also notice that 3s, 3p, and 3d have exactly the same energy. This only works if you're dealing with a one electron system like hydrogen or helium that has only one electron, or lithium that has lost 2 electrons, and so on. The question then is this: what are the orbital energies of multi-electron systems? To answer that question, please follow what I'm about to do properly. If you have a target made of orbitals as I have arranged on the right, and you are shooting arrows beginning from the lowest energy orbital up to the highest energy orbitals, your first arrow will strike the 1s orbital. What that means is that 1s orbital is the lowest energy orbital. So 1s is the lowest. If you shoot another arrow, it will strike the 2s orbital. So 1s is lower in energy than 2s orbital. If you shoot another arrow, the arrow will strike 2p and then 3s orbitals, which means 2s is less in energy than 2p, and 2p is lower in energy than 3s. If you shoot another arrow, it will strike 3p and then 4s. That means 3p orbital is lower in energy than 4s orbital. If you then fire another arrow, it will strike the 3d, then the 4p, then the 5s. This means that 3d is lower in energy than 4p, and 4p is lower in energy than 5s. And if you continue to shoot the arrows, you will continue to hit the orbital targets as I am indicating. This gives you an idea of how the orbitals in a multi-electron system are arranged. Let us now apply our knowledge to write the electronic configurations of the elements in the periodic table. Let us first take a look at hydrogen. Hydrogen has only one electron. The electron will go into the lowest energy possible, and the lowest energy possible is the 1s orbital. So the electron configuration for hydrogen will be 1s1. This means that one electron is located in the 1s orbital. Let us take a look at the second element, helium. Helium has a total of 2 electrons. However, the s orbital, the lowest energy orbital, can take up to 2 electrons. Remember, s orbitals can take 2 electrons. So, the electron configuration for helium will be 1s2, which means that 2 electrons are located in the 1s orbital. The next element is lithium. Lithium has a total of 3 electrons. The first 2 electrons in lithium will go into the lowest energy orbital in a lithium atom, and that will be 1s orbital. So the first 2 electrons will go into the 1s orbital. The remaining 1 electron will move on to the next orbital because, again, remember, s orbital can only take a maximum of 2 electrons. So this 1s orbital is now completely filled. So the remaining 1 electron will go into the 2s orbital. So it will be 2s1. Beryllium has 4 electrons. The first 2 electrons in beryllium will go into the 1s orbital. The remaining 2 electrons will go into the 2s orbital. Now the 2s orbital is also completely filled. Now let us move on to boron, which is the next element. Boron has 5 electrons. The first 2 electrons will go into the lowest energy orbital, which is the 1s orbital. The next 2 electrons will go into the 2s orbital. Now we have only one more electron, and 1s orbital and 2s orbital are completely filled. So we move on to the next orbital, which is the 2p orbital. The remaining 1 electron in boron will go into the 2p orbital. Carbon is the next element. Carbon has 6 electrons. The first 2 electrons will go into the 1s orbital. The next 2 electrons will go into the 2s orbital. The remaining 2 will go into the 2p orbital. And then we move on to nitrogen. Nitrogen has a total of 7 electrons. The first 2 electrons in nitrogen will go into the 1s orbital. The next 2 electrons will fill up the 2s orbital. The remaining 3 electrons will go into the 2p orbital. Now remember, 2p orbitals can take a maximum of 6 electrons. Remember that. So we move on to the next element, which is oxygen. Oxygen has 8 electrons. The first 2 electrons will go into the 1s orbital. The next 2 electrons will move on into the 2s orbital, and the remaining 4 will fit into the 2p orbital. After that, we have fluorine. Fluorine has 9 electrons. So it will be 1s2, 2s2, 2p5. If you add up all the electrons, you will see that they add up to 9. The next element is neon. Neon has 10 electrons. So the electron configuration will be 1s2, 2s2, 2p6. Now, if you're keeping a tab on the orbitals, which you should, you will see that the 2p orbital is now completely filled. Let us now move on to the next element, which is sodium. Sodium has 11 electrons. So the electron configuration will be 1s2, 2s2, 2p6. So far, I have used 10 electrons. The 2p orbital is now completely filled. I will need to move on to the next orbital, which is 3s. And for sodium, the remaining 1 electron will go into the 3s orbital. After sodium comes magnesium. Magnesium has 12 electrons. So the electron configuration will be 1s2, 2s2, 2p6, 3s2. But remember, 3s is a s orbital. It cannot take more than 2 electrons. So when we move on to the next element, which is aluminum, remember that the electron configuration will be 1s2, 2s2, 2p6, 3s2, because the s orbital is now completely filled, and the next electron, we move on to the next higher orbital, which is 3p. So it will be 3p1. After aluminum, we have silicon. The electron configuration will be 1s2, 2s2, 2p6, 3s2, 3p2. Remember, 3p is a p orbital. A p orbital can take up to 6 electrons. After silicon comes phosphorus. Phosphorus has 15 electrons. So it will be 1s2, 2s2, 2p6, 3s2, 3p3. After phosphorus comes sulfur. Sulfur has 16 electrons. So let us write the electron configuration. It will be 1s2, 2s2, 2p6, 3s2, 3p4. Why is it 3p4? Again, remember, 2 plus 2 plus 6 plus 2 plus 4 will give us 16. After sulfur comes chlorine. The electron configuration for chlorine will be 1s2, 2s2, 2p6, 3s2, 3p5. After chlorine comes argon. The electron configuration for argon is 1s2, 2s2, 2p6, 3s2, 3p6. Now 3p is a p orbital, which means it can only hold a maximum of 6 electrons. Let us now move on to the next orbital. After 3p comes 4s. So if we move on to the next element, which is potassium. Potassium has electron configuration of 1s2, 2s2, 2p6, 3s2, 3p6, 4s1. The remaining one electron will go into the 4s orbital. And calcium will have electron configuration of 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, etc. Let us now practice with some other elements that are just chosen randomly. Let us write the electron configuration for titanium. On the periodic table, titanium is element number 22, which means it has 22 electrons and 22 protons. So the electron configuration will be 1s2, 2s2, 2p6. So far, I've used only 10 electrons. 3s2, 3p6, 4s2. So far, I've used 20 electrons, and I have filled up the 4s orbital. The next orbital after 4s is 3d. Again, look at the directions of the arrow. After the 4s, then you move on to 3d. So the next orbital is 3d, and the remaining 2 electrons can fit into that 3d because a 3d orbital can take up to 10 electrons. Let us look at the electron configuration for bromine. Bromine has 35 electrons and 35 protons. So the electron configuration will be 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p5. Why is it 4p5? Let us add up all the electrons. We have 10 electrons here, another 10 electrons, another 10 electrons, making 30, and then 35. Let us write the electron configuration for tellurium. The electron configuration for tellurium will be 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10. So far, I have used 30 electrons. 4p6, because after 4p, then I move on to 5s. 5s2, 4d10, 5p4. Let us add up all the electrons to be sure that we are doing the right calculation. That is 10 electrons. From here to here, another 10. Another 10. That makes 30. This is 10. That is 40. This is 48. And 48 plus 4 will be 52. So we just fill in the electrons according to the energies of the orbitals, beginning from the lowest energy orbital, and we move on to the higher energy orbitals.